Okay, testing for cations. Remember, cations go to the cathode. The cathode is negative, so cations are positive. So typically metal ions. Almost without exception, they're metal ions, aren't they? So let's have a little look. And you get beautiful colours with some of these precipitates. That's going to be the giveaway. So metal ions, they form often colourful insoluble hydroxides. Okay, all they've got to do is find a hydroxide ion and choom, they form the precipitate. What are the steps? You put 3 centimeter cubed of the metal ion solution in a test tube. So if you're given the solid, then you would have to dissolve the solid in a bit of distilled water, put it in a test tube, add 2 centimeter cubed of sodium hydroxide solution, and look at what you get. Note any color change, you're going to get a precipitate, and you need to learn these. So if you get a light blue precipitate, it indicates the presence of copper 2 ions. What does the ionic equation look like? There you go. Okay. State symbols here are going to be important, and your solubility rules. There's a further test to see if it was copper ions, copper 2 ions. You add dilute ammonia solution and the precipitate redissolves to give a dark blue solution. So the precipitate, which is a solid, redissolves and you get a dark blue solution. It's dark blue, but it is transparent, so you can see through it. Okay, it's clear, but it's blue. If the precipitate you get when you add your sodium hydroxide is dirty green, then you had iron 2 ions present. Okay, what does the ionic equation look like? There you go. This is a dirty green precipitate. Gelatinous. It's kind of a chunky precipitate. The precipitate starts to go brown at the surface inside the test tube and on the sides of the test tube too because of atmospheric oxidation. So it gets oxidized from iron 2 to iron 3. Speaking of, if you get a rusty brown precipitate, then you had iron 3 ions present. That's the ionic equation. This is my iron 3 hydroxide, which is a rusty brown PPT. So in the previous one, when you get iron 2 hydroxide, the surface and on the inside walls of the test tube, they're exposed to oxygen, and the oxygen causes oxidation to iron 3 hydroxide. If you get a grey-green precipitate, then you had chromium 3 ions present. There's the ionic equation. Chromium 3 hydroxide is a grey-green precipitate. And this is an important note. The precipitate redissolves in excess sodium hydroxide solution to give a dark green solution, and it redissolves in excess ammonia solution to give a yellow or violet solution. And finally, if you get a white precipitate, then you could have aluminium, zinc, or calcium ions. And there's an example of the ionic equation. In the case of aluminium, it would be X3 plus, it would be Al3 plus, wouldn't it? And AlOH 3 times. So we have to work out how we're going to distinguish between these white precipitates. Okay, so what do we do? Well, first, the mixture that we have the precipitate in is split between 2 test tubes. To one of the test tubes we add excess sodium hydroxide, and to the other one we add excess ammonia solution. Right, let's have a look at the following table. So if it's calcium hydroxide, then it doesn't redissolve in either of the above, the sodium hydroxide or the ammonia solution. If it's aluminium hydroxide, it will redissolve in the sodium hydroxide, but it doesn't redissolve in the ammonia solution. And if it's zinc hydroxide, it redissolves in both. Okay. Now, important little mentions given to aluminium hydroxide and also to zinc hydroxide. These hydroxides, because they redissolve in excess sodium hydroxide, then that means that these hydroxides react with an alkali. But both of these hydroxides will react with an acid too to produce a salt. So we could say aluminium hydroxide and zinc hydroxide, they are amphoteric. They will react with an alkali and they will react with an acid. They're amphoteric. Okay, those are tests for cations. Have a look at these pages, read through them, and try the questions. Tests for gases. Now, all of these you've been doing for many years, so we're not going to dwell on them too much. A lighted wooden splint makes a popping sound, the famous squeaky pop, in a test tube of hydrogen. A glowing wooden splint relights in a test tube of oxygen. Oxygen is very reactive. It wants to react with anything it can get its hands on. Carbon dioxide, a lighted wooden splint will go out because it will extinguish it. There's no oxygen present. If you bubble the gas produced when you add an acid to a carbonate to produce carbon dioxide, if we bubble that carbon dioxide through lime water, which is calcium hydroxide solution, then we get a milky precipitate, don't we? We say it turns cloudy or it turns milky, and that proves the presence of carbon dioxide. Ammonia, you haven't really come across very much, but ammonia is an alkaline gas. It's got a characteristic sharp choking smell. It will make damp red litmus paper turn blue because it's alkaline. It will also form white smoky clouds of ammonium chloride with hydrogen chloride gas. And we saw this in year 10 with the diffusion experiment. So ammonia with hydrochloric acid or concentrated hydrochloric acid, which produces hydrogen chloride gas, will make ammonium chloride, which is a white smoke. Chlorine, it's a very good oxidizing agent, chlorine. It's got a sharp choking smell. It was used in chemical warfare, as you know. It will make damp blue litmus paper turn red. It's acidic. But then it bleaches it white. This is to do with it being an oxidizing agent. So chlorine bleaches things. It bleaches indicator paper white. Sulfur dioxide, nasty. It's actually a substance that can be oxidized by potassium manganate 7, which is purple or pink if it's got a low concentration. And a small amount of this potassium manganate 7 solution will go from purple or pink to colorless when it's shaken with a little of the sulfur dioxide. Okay? The sulfur dioxide reacts with potassium manganate 7 solution, which will decolorize. It goes from pink, purple to colorless. Have a look at the video of some of those gases. Okay, and read the pages indicated and try the questions. There's also practice questions at the end of the chapter. They should keep you busy. Now, before we finish, let's just remind ourselves of how we've collected gases in the lab. So when we did reaction rates, we collected gases like this, and we could measure how much gas was produced after a certain time. So this is another way of collecting gases. The gas that's produced is inside the syringe. So if this was hydrogen gas, it would be inside the syringe. So we can use a gas syringe to collect gases. But there are other more traditional ways. First one to look at is called downward delivery, for obvious reasons, or upward displacement because it displaces the air out of this tube. As it's going downwards, then you can guess here that the gas must be more dense than air, so it sinks. So think of gases that might be more dense than air. And there are 3 examples. You can do the maths if you want. The relative molecular mass, more or less, of air is a combination of nitrogen and oxygen, which is about 30. So carbon dioxide's got a relative molecular mass of 44, sulfur dioxide 64, hydrogen chloride 36.5, so they're all more dense than air. Important thing to think about here is that you have to use this method, especially for sulfur dioxide and hydrogen chloride, because they're so soluble in water. So we can't collect them if there's any kind of contact with water. We'll talk about that in a second. Upward delivery, downward displacement of the gas inside the tube, we can do with gases of low density. And you can guess which ones we're going to talk about here. Hydrogen's the obvious one, and even ammonia can be collected like this because it's got a relative molecular mass less than that of air. Okay? And the last one, the one that you've done the most in the lab, is over water. So you produce the gas, you bubble it into, this is a lovely old-fashioned beehive shelf, so any bubbles here come out of this hole, they go into my gas jar, the gas collects here, and the water's slowly displaced. And gases we've done this a lot, but we've done it with gases that are not soluble or not very soluble in water. So the classic ones are hydrogen and oxygen. They're not very soluble in water. You can also do this with carbon dioxide. It's not too soluble in water. Okay, so downward delivery, upward delivery, and over water.